Okay, today we discuss about operation amplifier, different types of practical, and then we simulate this practical in a Proteus environment. First of all, number one practical is known as offset voltage measurement. Offset voltage measurement of op-amp, and then calculate four parameters. The four parameter names are the basic parameter, which are also known as the basic parameter for study any operational amplifier characteristics. First of all, the first parameter is known as input offset voltage. This is also known as VIO. Okay. Then we measure input base current 1. Then we measure input base current 2. And after all, in the last is the most important, that means input offset current. These four parameters are very important for measurement of the operation amplifier. Okay. Now second practical is our to study about different types of amplifier. Different types of amplifier. As we discussed in the previous lecture, say for example, inverting amplifier, then non-inverting amplifier. Number C is unity gain buffer. Okay. Number D is adder, or also known as summing amplifier. Number E is differential amplifier, also called substructor. F is known as log amplifier. In the G, we study about anti-log amplifier also. And then the non-linear operation. For the non-linear operation, we study about comparator and Smith trigger. So these are very important. Okay. So this is the second practical of operation amplifier. In a third, there are different types of filter circuit, like low pass filter, high pass filter, okay, band pass filter. Different types of filter circuit are designed by this operation amplifier. And in the fourth, we study about CMRR and slew rate and different types of other parameter in the operation amplifier. So now we talk about our first practical today. Find the offset voltage measurement for op-amp. For this measurement, we follow this circuit. This is an operation amplifier which is biased by plus VAC and minus VAC. Practically, this is a plus 12 volt and this is a minus 12 volt. And here we connected two resistance which named as R1, and here one resistance is connected known as 1 mega ohm resistance, and here we connected another resistance 1 mega ohm resistance. This resistance is connected to flow microampere level current in inverting and non-inverting terminal. That's why we connected 1 mega ohm resistance, and this is R1 and R2. Please listen carefully. This is output voltage V0, and when these two resistors are short circuited, then the output voltage is known as V01. Okay, first note down, when these two resistors are get short circuited, that is, we say that these resistors are named as R3. So when R3 is equals to 0 ohm, that means, okay, this is named as R4. Okay, so when R3 R4 both equal to 0 ohm, that is short circuited, then the output voltage getting here is known as V01. Okay, in the same circuit, again we draw the operation amplifier again, and here present R3 and these R1 resistance and these R2 resistance, and now R4 is short circuited. Okay, now in this situation, the voltage at the output is known as V02. This is the second circuit. In the third circuit, again we draw the same circuit. There is no change, but one simple changes, that is, now R3 is short circuited, R4 is present. Now at this condition, the output voltage getting from here is called V03. And number 4 is when both resistance are present, when these both resistance are present in inverting and non-inverting terminal, this is R1, this is R3, this is R4, and this is R2. And at this situation, the output voltage getting from here is known as V04. So there are 4 voltages are coming out: V01, V02, V03 and V04 for different circuitry. Now one thing should be remembered, that our task is to measure VIO, which is given by the mathematical relationship R1 into V01 into 10 to the power 3, because in a millivolt range, R1 plus R2. So now we know all these values, and from the first circuit we know the V01 values. So putting here V01, and we get our first parameter VIO, that is input offset voltage. Number B, we calculate the second parameter, our second parameter, that is input base current IB1, which is given by the mathematical formula V02 minus V01 divided by R3 divided by 1 plus R2 by R1. All parameters are the known parameter from this circuit. These are R1, R2 is basically select by the user defined, either 10K, 1K or anything in it. And number C is another base current formula IB2, which is given by the mathematical relationship V03 minus V01 R3 divided by 1 plus R2 by R1 into 10 to the power 9, because this is in a microampere level, nanoampere level. That's why 10 to the power 9 is included here for the dimension. And last one, input offset current. Okay, this formula is basically V04 minus V01 divided by R3 divided by 1 plus R2 by R1. This formula is very important, otherwise we don't get any idea about how to measure this current. Okay, so that's why this is very important. So these 3 parameters are in a nanoampere and these are in millivolt. So how we take this value V01? So we make the first this circuit, and for example, here we measure for different R1 R2 value. Say for example the ratio equal to 1K 3.3K, say for example, then 1K 2.2K for different selecting resistance, then 2.2K and 10K and so on. For different values of resistance, we get different values of V01, V0 number 1, 2, 3, 4, 5 up to 10 or 20 values. Then we get average these values, and after averaging these values, we put here our value V01. Okay, and this is same for V02, V03 and V04 also. So here one thing should be remembered, here R1 R2 is not a single value. We take the different values, lots of combinations are taken here for the, and after this the average this value and putting this value here, that is shown here, that is V02 minus V01. Okay, so where V02 is getting from this circuit, we get the value of V02. From this circuit we get the value of V03, and from this circuit we get the value of V04. Now putting this value here, and then after this we getting our 4 parameter, the basic parameter of the operation amplifier, which is known as offset value measurement in operation amplifier. Okay, now we design this 4 circuit which is discussed in this slide. This is the first circuit to measure V01, second circuit V02, third circuit measure V03 and V04. So we may implement this circuit in a Proteus environment software simulation. So first we're taking one operation amplifier known as 741, which is known as this operation amplifier 741. I already take here 741, and then take the resistance. Here resistance is available resistance, and please take 0.6 watt metal film resistance, anyone getting from here. Okay, I already taken this element. Okay, so now for starting, place this operation amplifier here, and then click here. From the power module we take 2 power module. Okay, 2 power for biasing this operation amplifier. One is connected pin number 4, and another is connected pin number 7. and double click here and mention this is a plus 12 volt, and again double click here, mention minus 12 volt. Okay, now we connecting the resistance, different value of resistance. This is resistance R1, this is resistance R4. So for the first circuit we see that R3 R4 is getting short circuit. For the first circuit we show that here two resistance get short circuited. Okay, so that is, this is the short circuited and this is a short circuited. Okay, so now only two resistance are connected here, R1 R2 only, because no R3 and R4 are present here. So now R1 R2 are connected for the gain. Some gain are mentioned here. The gain is, say for example, this is 1K, and double click here, this is 10K. Okay, so now this is connected in an inverting terminal. See that this is connected in an inverting terminal and non-inverting is grounded. So now we take ground here. This is a ground pin. From this pin we connect from R1 to R1, and one is connected to R3. Okay, and now one voltmeter is connected. Voltmeter is taken from here. Now voltmeter is placed here, and again this negative terminal is connected to the ground. Okay, now this is our complete circuit. Okay, so sorry, this is a 10K value. Now run the simulation and see that the voltage equal to 0.01 volt. One thing should be remembered, we measured in a millivolt range, so that's why double click the voltmeter and select in a millivolt range. Okay, and then okay, and then run again simulation. See that these are some error voltage are V01 getting at the output, whose magnitude equal to 12.5 millivolt approximately. Okay, so now we changes this resistance value. Say for example, the gain equals to, so this name equal to basically R2. We mention here the name equal to R2, and this value equals to say 3.3 kilo ohm. Okay, for the different value, again run the simulation. So now and here some table are mentioned. These R1 value, sorry, these R1 value, and this is R2 value, and for this 1K, for this 10K, and this is, here we mention our output voltage, whose name is, yes right, V01, and we mention here for V01 what is the value we getting, 12.8 millivolt. Okay, so this V01 in a bracket, please mention this is a millivolt range. Sorry, this is in a millivolt range. Okay, and now for the second value for 1K, this is for, this table is used for your practical purpose to measure the value of these different types of V01 voltage, 4.83 voltage. Okay, so now for the another combination, say for here 3.3 kilo ohm and here, and one thing should be remembered, always R2 greater than R1. Okay, because we need some gain. So this is the implementation of this first circuit. Okay, so this is very easy to implement. So our first circuit is implemented. Okay, now for the second circuit, select this whole circuit and press here, copy to clipboard, and then paste from clipboard. Now second circuit is placed here. Now for the second circuit, what is our requirement? Our requirement is only connected R3 resistance. Okay, only connected R3 resistance. So R3 is connected inverting terminal. So again select the component mode and place the resistance here and connect it to this terminal, sorry, this terminal, and one terminal connect is here, and this value equals to 1 mega ohm. Okay, 1 meg, 1 m. Okay, now run the simulation and see that. Okay, now this is mentioned that these are 391 millivolt. Okay, so for the another combination, say for example, this is for 3.3 kilo ohm. If we change here 10k value, 10k value, then again run the simulation and see that this is 999 millivolt approximately. So this is the value of V02 voltage for this second circuit. And now for the third circuit and fourth circuit, both are implemented in the Proteus. Students, please do it yourself. These are very easy to implement this circuit in this Proteus simulation. Okay, and getting the value of V01, V02, V03 and V04, and put here for different value of Vi0. For V01, for V01 first value, that is from this table. From this table, for the first value we getting the first Vi0. Now for the second value we getting the second Vi0. Say for example you take the 10 different values are taking for Vi0, and then after getting you average of these values and getting the final Vi0, and same for IB1, IB2 and II0 respectively. Okay, now we study the next circuit hour, that is implement different types of amplifier like inverting, non-inverting amplifier. So basically you know that, also know that for inverting amplifier, this is a circuit diagram. One resistance is connected here named as R1, this is R2, and here R2 value is always greater than R1, otherwise it cannot work as an amplifier. Okay, and here we connected one AC signal or DC signal, any one, and op-amp should be biasing plus 12 volt and minus 12 volt, and these output. And here V input, for different V input we measure different and mention here for, say for example, R1 equal to 1 kilo ohm and R2 equal to 2 kilo ohm. Okay, say for example, so the gain equals to basically 2. Okay, so now for different input voltage we get the output voltage. So this is known as inverting amplifier. So for non-inverting amplifier, what is the circuit? The circuit diagram is, this is inverting, this is non-inverting. There is an feedback is connected for the closed loop response. This is R1, R2, these are grounded, and AC signal is applied here, and this is output. Okay, now when this signal is applied at non-inverting terminal, then the output voltage equals to, you already know that, 1 plus R2 by R1. In the previous video we discussed about that. So now again from here the same thing, for the different input voltage we measure different output voltage. Okay, now for the error circuit we already know that this is the different circuit of the operation amplifier. Now for the error circuit there are 3 resistors are connected. Okay, so now there is a feedback is also present, and here 3 different voltage V1, V2, V3 are applied, and these all resistance are R1 and these R2, and we get the V0. Okay, so this circuit we already know in, and we discussed in the previous lecture. Now we implement this circuit in this Proteus environment. Okay, so now for this, first of all, here we changes some component. So first of all, here delete this line and delete this line, and feedback must be present. The non-inverting is grounded, because from this circuit we see that non-inverting is grounded. And now we take one signal generator. Now say for example, this is a signal generator is connected, the plus terminal is connected here and minus terminal is connected from here. Okay, so, and these are signal generator properties, and the gain equals to should be 2, because you consider the gain equal to 2. Okay, and this inverting terminal is connected from here to here from this diagram. Okay, between R1 and R2. Okay, now these 1K and these 2K. Now we connect one CRO here, that is cathode ray oscilloscope, or we connect digital storage oscilloscope, that is taken from here oscilloscope. So the yellow line is connected to the output, and the blue line, the two channels are connected, and run the simulation. First save it and then run the simulation. They have some problem with the DLL. The problem is okay, right click here and then edit properties and press click here, attach hierarchy module, and then okay, and then run the simulation. But there is some problem. Okay, delete this signal generator and connect from here. These are voltage, not from here. Okay, now these are sinusoidal waveform. Now this sinusoidal waveform is connected in the inverting input. Okay, sorry, the inverting input. Okay, now the amplitude equal to, here show that the amplitude equal to 1 volt, frequency equal to 1 hertz, but we increase the frequency, that is frequency equal to 1000 hertz, that is 1 kilohertz. Okay, the sine wave, and the amplitude equal to 1 volt. Now click OK and run the simulation. Now this is okay. Now see that this is our channel. The blue channel is connected at the inverting and yellow line connected at the output. Okay, so this is the output waveform for the operation amplifier output. Our circuit is R1, R2. R1 is connected to inverting terminal, and the R2 is connected to output, and number 3 is connected to the ground. But there is a problem to show the output. Yes, now there is a problem in the simulation environment. Now see that, but okay, now we changes the frequency, say for 500 hertz. Okay, now again run the simulation. Now see that, stop this simulation. Now see that, what is amplitude, how to measure it. Now from here, cursor is, click this cursor, and this is a control panel of this oscilloscope, from where we calculate our amplitude and the frequency also. Now here one cursor, another cursor. Now see the difference between them, approximately 1 volt, and now here and here this cursor. Okay, now see that what is the magnitude difference. So basically with respect to the input, the output is basically 2 times of the input. Okay, so that's why it is used as an inverting amplifier mode. Okay, and here one thing noted, that the input and the output is phase difference, because this is an inverting amplifier. So that's why when input goes to negative, then output goes to positive. Okay, and vice versa. So that's why it is known as inverting amplifier, that is output and input are 180 degree phase shift. Okay, we already know from the theoretical concept of the operation amplifier for inverting amplifier concept. Okay, so now this is an output response of inverting amplifier. We show here that and for different values, say if we change this value from 2K to 4K, now see that what is the changes at the output. There is some problem in the simulation. Okay, gain is not too much increasing. If we see that this is a 3K, then what is the simulation output? Okay, now see that this is okay. These are 3 times. Now this is minus 2.9 volt to plus approximate 2.95. Okay, that is equal to equivalent to 3 volt. Okay, and from here this is lower part equal to minus 950 millivolt, that is equal to 1 volt, and these output, these one thing, this line is to vary this position. We can variation of this signal from the screen. Now see that the amplitude is approximately 900 millivolt, that is approximately 1 volt. Okay, now if this input equal to 900, then multiply into 3, that is equivalent to approximate 2.9 volt or equivalent to 3 volt also. So both positive and in the negative, both positive in the negative, because from here this is also show that if we take cursor, then it is also show that this is negative amplitude goes to approximate 1 volt values. Okay, and positive also 1 volt. So peak to peak is basically 2 volt, and this is peak to peak equal to 6 volt, because this is our baseline, this is our baseline 0 volt. Okay, sure, this is a 0 volt baseline. Now from this 0 volt, this is a negative 3 volt and this is a positive 3 volt. Now peak to peak is 6 volt. Okay, so now using this cursor, we measure the proper amplitude and proper peak to peak value for this practical measurement. Okay, okay, now for the second circuit, to implement the non-inverting amplifier. So first of all, delete this wire from this ground. This 1K should be connected in the ground terminal, and here we apply the DC voltage or AC voltage, anyone, but here we apply DC voltage. Now say for example this is a DC voltage. Okay, and you connect one potentiometer, because we vary the input voltage, and for different input voltage you show the output voltage magnitude. DC voltmeter is connected from the output terminal. Now these are connected from the output terminal, and another DC voltage is connected here to measure the input voltage, non-inverting terminal. Okay, now run the simulation and see that first of all this is equal to 0 and this is equal to 0, and if we increase this voltage, okay, one thing should be remembered here, DC magnitude equals to 0 volt, increase this and it equals to 12 volt. Okay, now see that. Okay, now when the input voltage equals to very low voltage, that is 0.6 volt, the output equal to 2.4, but these are same phase, positive and positive. Why? Because the gain equals to 1 and 3, and for a non-inverting amplifier we see that what is again 1 plus R2 by R1. So here R2 equal to 3K and R1 1K, so therefore 1 plus 3, that is 4 times of, that is 0.6 into 4, that is 2.4. Now if we increase this voltage 0.7, then 2.88, now increase this voltage 8.84. now see that now for different types of voltage we measure the output voltage for, and one thing should be remembered, the op-amp is saturated at plus 12 volt. So if we increase further, but this is a problem in a simulation, because in a simulation any voltage is shown as the output, but in a practical we cannot get beyond the plus 12 volt, because the op-amp is biased from plus 12 to minus 12. So this is a simulation error. Okay, practically plus 15.48 volt is not coming, because its highest voltage magnitude plus 12 volt. Okay, and then if we increase this voltage, input voltage say 4 5, then output always remains constant, that is plus 12 volt, and this is same for the negative voltage also. Okay, so this is the diagrammatical representation and the simulation representation of, and also the circuit diagram representation of non-inverting amplifier in a Proteus environment. Okay, now we implement the error circuit. For error circuit, this is our error circuit. 3 resistors are connected at the input. Now for the error circuit, what we can do? So first of all, we delete all the component here. Stop the simulation first, and then delete this component, and we draw this circuit again. So there is a problem in a simulation. Okay, now again we open the simulator and delete this component. The voltmeter also deleted, and these were, now this is connected to the inverting terminal, and from the diagram we see that non-inverting terminal is grounded. So now non-inverting terminal is first grounded, and this voltmeter also grounded at this ground terminal. Okay, now 3 resistors are connected at the input. Okay, separate three resistance. This is number 1 resistance, this is number 2, this is number 3, and all resistance equals to, say for example, this value of 1k, and another resistance, this value equals to 1k, and then this is a value of again 1k. Okay, and these resistors are connected to inverting terminal, this terminal, and again this terminal. Okay, three resistors are connected. And for DC voltage, we again select the DC input voltage. These are the DC voltage, sorry, now this is the DC voltage. From here we getting the DC voltage. Yes, right, from here. Now 3 potentiometer are connected, number 1, number 2, and number 3, because 3 input voltage. This is all are connected to the common terminal, because all are connected to plus bar volt, and changes this volt. This is equal to 12 volt approximately. Okay, now these 3 terminal are gets short circuited, okay, and connected to the main ground, and the second terminal of each potentiometer is connected to this resistance. Okay, now these are complete this circuit. Okay, next we connect 3 voltmeter separately, number 1, number 2, and number 3, for showing 3 different input voltage. This is number 1 connection, this is number 2 connection from here, and this is number 3 connection from here. Okay, that is pin number 2 of potentiometer, or middle pin of the potentiometer. Okay, now run the simulation. First save this program. Okay, now run the simulation and see that, and decrease the first, we decrease the input voltage, we decrease the input voltage. Now this is decrease the input voltage, say this is input voltage of 1.6 approximately. Now we 0.57, this is 1.5, 1.4, this is 0.46. now if we, now this is also getting very low. Now 0.6 plus 0.4 plus 0.6, 1 volt approximately, 1 plus 1.5. So 3 summation of 3 voltage, input voltage 1.5, and 1.5 into 3, yes, that is 4.5, and this is minus 5.1 because it is not exactly 4.5. Okay, now what is exactly input voltage? We help with the help of calculator. 0.46 plus 0.68, sorry, 0.46 plus 0.68 plus 0.57. So exact voltage is 1.71. Okay, into 3, that is equal to 5.13. So that's why here 5.11, and this is negative. Why negative? Because in the diagram show that this is inverting type adder. Okay, that's why it is minus 5.11 voltage is shown here. Now for the another input voltage, say for this input voltage varies some amount of increase, this is 1 volt. Okay, now what is the summation of this input voltage? Now clear this calculator first. 0.46 plus 0.68 plus 1 volt, so this is 2.14. so 2.14 into 3, that is equal to 6.42. now see that there have some error. Okay, practically it is not equal to 6.42 exactly, so that's why it is minus 6.39. so that's why for different input voltage variation the output gets different output voltages. So that is the importance of adder. So we see that here we addition of 3 voltage, and if one thing should be remembered, and if this is basically known as summing amplifier, and if this resistance equal to 1k, then the gain equal to 1, then we just addition of this voltage. Okay, now see that this addition of this voltage. So what is our input voltage after addition of this 3 voltage? We get 2.14. okay, so here we see that this minus 2.13. so when both R2 and R1 equals to 1, then it's only summation of this 3 voltage, and in this situation this circuit is known as adder. And the previous circuit, when the gain is present, this circuit is known as summing amplifier, because first summing the 3 input and then amplify, and then the amplified DC voltage is shown across at this voltmeter. Okay, so this is a practical circuit of adder or summing amplifier in Proteus environment. Now for the differentiator circuit. Okay, now we discuss about differentiator circuit. So for differentiator circuit, there is a circuit diagram of differentiator. This one resistance is connected and there is a feedback resistance, and here one potential divider is applied. Here V1 and V2 voltage are applied, two difference voltages. These R1, R2, these R1 and R2, and when R1 is less than R2, then it is known as differential amplifier, and if R1 equal to R2, then this is known as subtraction, because this circuit output equals to V1 minus V2. So this is a subtraction of these two voltage at the output. So that's why it is named as subtractor. So this circuit always implement in this Proteus environment and show the output voltage waveform. And this is also known as unity gain buffer circuit. And for unity gain buffer circuit, inverting and output are short circuited, and we apply here AC or DC voltage any one, then V output equal to V input. This circuit is basically used for impedance matching. Okay, because the input impedance of the operational amplifier, that is equal to Ri equal to infinite, and output resistance that is approximately equal to 0. So this circuit is the very best choice for selecting the impedance matching circuit. And next, another circuit is logarithmic amplifier. These are resistance and there is a diode is present, and there is a potentiometer is connected, as we already show that how potentiometer connected in the Proteus. Okay, and for anti-log amplifier, these are anti-log amplifier. In the previous lecture, in the theoretical class, we discussed about these different types of amplifier in operation using this operation amplifier. Okay, basically operation amplifier is analog computation. So using this circuit, we can analog compute of this input voltage present at the output. Okay, now this circuit is also implement this Proteus environment. Okay, so now it is your homework to implement the other circuit that is differentiator log, anti-log, and also comparator and Smith trigger for comparator and Smith trigger purposes. This is a circuit diagram of comparator. This is a circuit diagram of comparator. One generator is connected, and here plus bar 12 volt, and this terminal is connected from here, and here one potentiometer is connected and connected to the inverting terminal. This is a plus VC, this is a minus VC, and to study the variation of input versus output. Okay, so this is a comparator circuit, nonlinear operation of the operation amplifier. And for Smith trigger circuit, this is a Smith trigger. This is same as a comparator bar 1, but here one difference. Here two resistance are present, one is R2 and R1, and here also connected one potentiometer to vary this input voltage. This is a ground, this is a plus VEC, this is plus VEC, and these resistance are for safety resistance of the Zener diode and output V0. And here also we vary the V input versus V output voltage. Okay, and to study the output behavior and how output changes with respect to the input. And this circuit also implement in this Proteus environment. Okay, and to study and to implement this circuit. For example, if we implement this circuit, say for example, first of all we delete this component first. So one voltmeter is connected here, and here we take one Zener diode. Okay, one Zener diode. So any Zener diode, say for 5.6 volt Zener diode is taking, our reference voltage is 5.6, so that's why we used 5.6 voltage Zener, and this is connected in a non-inverting terminal. Another terminal is grounded. This resistance is connected to plus VEC for Zener safety resistance, and say for this is equal to 1K. Okay, this value equal to 1K. Okay, and now one potentiometer is connected to the non-inverting terminal, as we mentioned in this diagram. Okay, inverting terminal is connected to the middle line of the pot, and this is connected to plus VEC, and voltmeter is connected to show the input voltage magnitude. Okay, now see that what is the effect of comparator. The comparator theory is that when this inverting voltage is greater than non-inverting voltage, output is switched to minus VEC, and if non-inverting greater than inverting, the output is switches to plus VEC. Now see that it is it true or false. Okay, now for this simulation, now save this circuit, run the simulation and see that the voltage equal to maximum. But one thing, this voltage equal to the voltage dimension. Okay, so first of all vary, but now here, so see that when input voltage is 8.4 approximately, then the output is, this output is basically some error is shown in the simulation, because this is shown minus 12 volt, because here inverting voltage is 8.4 and Zener voltage is 5.6. okay, if you watch the Zener voltage properly, appropriately, what is a voltage drop across the Zener diode. Now see the one extra voltmeter is connected from here to here, and to see that, oh, this is a basically, no, from, there is a wrong connection, this is a wrong connection, they connected from here. Okay, now see that this is a 5.5 bit, that is equal to 5.6 volt. Now when input is greater than, inverting is greater than 5.5, so what is our theory? The theory is that minus, output is minus. This voltage is basically not properly shown, this is a minus 12 volt. Okay, and when input is lower, then output is switches, but here some problem arises because output is not switches, because there is an error of simulation. What will be the error? The input is 2.2 and the output is this, so Zener diode getting the voltage 5.5. okay, now if we increase this resistance for, say, for 3K, what will be the effect? Now effect is, okay, now there is a no effect, no changes of, there is no changes. Now if we changes this operation amplifier, there are different types of op amps are available. Okay, now if we changes this operation amplifier, now see what is happening. Now for the another operation amplifier, for 741 operation amplifier, for 741, there are lots of 741. Say here we type op amp. Now this is one operation amplifier. Okay, now we take this operation amplifier and connect, this is a plus 12 volt and this is minus 12 volt. Okay, inverting connected to this potentiometer terminal, number 3 is connected to Zener diode, and this is the output. Now see that what is the effect? This is a minus 19 volt. No, this is not a, this output is not properly shown in the simulation, because I don't know what is the error. Okay, because here two messages are shown. Okay, in this, to run this project, just for the from the concept of theoretically, and if you done this practically in a breadboard or Fedor board, then when inverting is greater than non-inverting, output is switches to minus 12 volt, and when non-inverting is greater than inverting, the output is switches to plus 12 volt. So this is the appropriate value. Okay, this is not shown the appropriate value of the, for this circuit. Okay.